Let's see here. Let me just move forward. Oh, by the way, so I'm from Oak Ridge National Lab. Name's Raphael Pooser. I lead a group there. This is how pretty it is around there. We need people. So if you go to that website I've got listed there and search for quantum. In fact, we need people even to take my job. So as Chris mentioned, I'm a group leader and a distinguished research scientist, and turns out it's kind of hard to be both. So I would like somebody to come in and be a group leader. So if you want to be my boss, go there and apply. I hear that I can be quite difficult though as a subordinate. So all right, so we've got the Quantum Science Center over there at Oak Ridge as well. So the Quantum Science Center, I need to give a quick intro to this. You know, every talk I give now has to talk about this a little bit because it's sort of our biggest thing going on in quantum information. We're looking at quantum materials, studying quantum information processing with new quantum materials, and even trying to figure out what is dark matter made of. So we're trying to study almost everything in the universe. It's a pretty difficult task to lead that center. Luckily, I'm not leading it, but I'm a part of it. And some of the work I'm talking about is in there. Okay, here's this group that we mentioned before, and we're doing a lot of stuff in this group. We'll talk about a subset of it. We got ion traps in this group. We got atomic physics in this group. Hopefully you can see my mouse. We got micro cantilevers in this group. And then this background over here, we're even doing integrated optics. So all these kind of quantum sensor stuff, we're trying to like cram them down onto chips. So yeah, we've got large ambitions, about 8 people in the group right now. Need more people to do all those ambitious things. That's why we're hiring. So just more pretty pictures of what's going on in the group. And we have a bunch of optics for trying to build quantum sensors out of ions, building quantum sensors out of optics, building quantum sensors out of integrated optics, quantum sensors out of cantilevers, so on and so forth. So I'll go over a subset of these. We've got some transitions. Okay, so, and we're working with some interesting folks. I mentioned this idea. We're not going to talk a lot about it in this talk, but we're even studying how to use quantum sensing to try to detect dark matter. And here's the list of borderline criminal people helping us do it. Just kidding. This is a bunch of upstanding citizens helping us study dark matter, quantum sensing for dark matter. So go check out this website. It's pretty interesting. That's one of the big projects going on in the Quantum Science Center. So all the physics that I'm going to describe here is can be used not only to detect things at the nanoscale, which is what I'm dealing with in this talk, but also at the cosmic scales, looking for gravitational waves and so on to try to detect dark matter. So we're talking mainly about using entanglement to make sensors. So that's our kind of, we do all of these things in the quantum information science section at the lab and in the Quantum Science Center, but this talk is mainly going to be talking about entanglement and sensing. Okay, so what kind of entanglement? Here we're talking about these kind of unphysical, but well, if you stick a constant that depends on X or P in front of them, they become normalizable. These quantum states here, so these are continuous variable wave functions. So this is we'll call this position or amplitude, and we'll call this momentum or phase, and these are Fourier transform of one another, right? So this is sort of the entangled state that you might know and love if you were to represent it as light switches or spins, a Bell state. This is what this is talking about, is the continuous variable version of that. And that showed up in this paper in 1935, which I think Dan alluded to in the last talk, actually. So this is the EPR state after Einstein, Podolsky, and Rosen. So sort of the original idea is, okay, quantum mechanics doesn't seem right. It allows us to write down states like this, and it appears that we can have lower noise in specific variables when we do some measurements on these subsystems than otherwise would have been implied by the Heisenberg uncertainty principle. Of course, that's not an issue. There really isn't any violation of Heisenberg uncertainty principle with states like this. But there is sort of squishing around of the noise off of one variable and into another, depending on how you arrange the noise, or how you arrange the state. So we call those squishy states squeeze states. And so we're going to talk about how to use that for sensing in a second here. So this is my sort of 20,000 foot view of a sensor. And typically what I'm dealing with is there's noise in these various pieces, maybe in the readout, or in the process of transducing information, or in the process of transducing the readout into some electrical signal, or even in the electrical signal that goes to the computer. And so our job, at least for the stuff that's in this talk, is how do we reduce the noise in some of these things to improve the signal to noise ratio. And so I've got one definition here. Let's see. It says, okay, so the fundamental detection limit is determined in many systems by the quantum mechanics, and I'll call that a quantum sensor if I can find a way to manipulate that noise level. From operating at these fundamental noise limits as dictated by, say, the Heisenberg uncertainty principle, I'm doing things to try to offload noise from one variable into another. I'll call that a quantum sensor. That's just one definition of a quantum sensor, of course. So that's what we're working with here. Okay, so of course, this isn't my idea. Just in case I'm making it sound like it's a very smart thing to do, it's because a very smart guy came up with it, who is not me, Carl Caves in 1980. And actually, just as was alluded to in the previous talk, the idea here was, let's try to use this squishy noise that I was talking about to look for gravitational waves in interferometry. Of course, there's been, since 1980, there's been quite a bit of research now into using quantum noise reduction, which is the technical term for squeeze states, to do quantum sensing since then. So that's what we're talking about here. So what is quantum noise reduction? So actually, without doing any math, I'll just think about it in terms of statistics of light and thinking about photons arriving on a detector. There's some coherent state has some distribution of photons in time. And so then the photocurrent on a scope has some fuzziness to it. And it turns out that the distribution of photons in a coherent state as it hits the detector has some fundamental limit to it. And we'll call this a shot noise limit. And of course, that limit is just really determined by the fact that it's a minimum uncertainty state, right? So delta x equals delta p. Of course, delta x doesn't have to equal delta p for minimum uncertainty states. So the squeezed states, which are more general, say you can have a different noise than the coherent state in one variable versus another. So let's say for intensity, again, thinking about photons arriving on a detector, let's just say that we could order them, put them more ordered in time. If they're more ordered in time, then the statistics have smaller variance, right? And so you have less fuzziness on your scope. So that's the sort of the quick and easy explanation of how you might get squeezing in the lab and what effect it might have. So if you can play games with the statistics of the light, you can have less noise in your measurements. And so one way to do that is to use nonlinear optics. That's why I've got this bullet at the bottom. Amount of quantum noise reduction increases with the strength of nonlinearities. Oops. So once you have that thing, so here's a pretty picture from some review papers we wrote recently on this topic. Well, okay, stick it in a microscope and have lower noise on the readout. So this is like an AFM cantilever or something, or a confocal microscope. And so we've done a few of those kinds of things, which we'll talk about in a second. So yeah, I don't have time to go through all the little call out boxes in here, but it's in this paper here, Trends in Chemistry. And then we also wrote a review on using quantum noise reduction and other things like correlated photons that we're talking about in the last talk in this Chem Reviews that was published recently. So you can check that as well. So here's how we make it. We take some light and shine it into a atomic vapor. I have this energy level diagram here at the D1 line in this rubidium vapor. And we absorb some of that light that goes in, and we stimulate emission on a separate frequency that's offset by the hyperfine ground state splitting at that line. And because of this difference in energy at the hyperfine ground state, we emit another photon from a virtual level. So this process is called Fourier mixing, and these two guys are correlated. So if we emit them one photon at a time here, you get one photon at a time here. And so you can see how if you're emitting photons in pairs, their statistics are now correlated. So this is sort of a very high level explanation of how you can get this sort of effect. Sorry for these transitions, forgot about those. Okay, so yeah, and here's a picture of just what it looks like, actual noise looks like. If you measure these correlations, here's this blue line, the coherent state, noise decomposed into frequency. And here's the noise of these two beams combined in a joint measurement, which is some level below, as we decompose in frequency, some level below the blue line. So it means we've squished some of the noise out of in this case, the difference in intensities onto the phase, and we're measuring the difference in intensity. So we're accessing that lower noise level. This is just what it actually is. This is what the actual noise is in these squeeze states. So eta is detection efficiency, G is the nonlinear gain inside this medium. And so for any G greater than 1 and eta greater than 0, where 1 is units of shot noise, this right-hand side is always less than 1. So all we got to do is build a system that has a G greater than 1 and then eta greater than 0, and we can have less noise in measurements of intensity. Okay, so great. So that's what this thing does. So let's use it to do some sensing. Oh, but before I do that, we talked about the fact that this should be useful for phase sensing in the previous talk, and that's right. And actually, there were proposals and since then many demonstrations of using nonlinear interferometers to do phase sensing. So you take a regular interferometer, you replace the beam splitter with this thing, and this thing looks like a nonlinear beam splitter. I think this photon goes right, this photon goes left, right? So this looks like a nonlinear beam splitter. As a beam splitter with gain, with gain. Well, you can actually build such a thing, and if you do build such a thing, you again obtain better SNR than a classical interferometer, as according to the nonlinear gain. Now, the reason for this improvement is actually because these photons here that come out in these two arms of the interferometer are entangled with each other. And for more information about why that works, you can check out this, yet again, another Carl Caves paper, only 40 years later. Again, a quantum sensing paper from Carl Caves. It's quite interesting about using this phase sensing technique over classical interferometry. So we've implemented that a few times. There's some papers on making nonlinear interferometers. Okay, I better hurry along here, talk about using it for sensing, because I think I only have like 5 minutes or so left. So how do you use it for sensing? So you take these entangled beams of light and stick them in whatever it is that you're trying to transduce, and then try to access the noise reduction that's present in these quantum fields. So actually, in this case, this picture here, it looks a little bit complex, but it's doing a phase sensitive measurement with these beam splitters and detectors. It's called homodyne detection. So one guy picks up a phase and the other guy acts as a phase reference, and this acts as the beam splitter, right? So this is a nonlinear interferometer that accesses a phase given onto this guy by this transducer here. The transducer in all of our experiments, you know, the microcantilevers, magnetic field rotations, magneto-optical rotations, extraordinary optical transmission, plasmonics. And just to show we're still, a lot of the work I talk about is older, but we still have some stuff coming out on this even just a month ago on using this for magneto-optical rotation in a cryogenic microscope. But the same exact kind of setup. It's nonlinear interferometric readout of magneto-optical rotation in a cryogenic microscope. So really, I think one of the things that are interesting for some of our collaborators at Duke or potential collaborators at Duke is using these things to probe nanophotonics using plasmonics. So we've got Kretschmann configuration in which you excite surface plasmon polaritons, and this other thing called extraordinary optical transmission, where plasmonic films actually annihilate photons on one side, plasmons couple on either side of the film, and then re-emit coherently those same photons, re-emit new photons on the other side of the film. You can use both of these things for sensing. So, so this is an example of using it in a cantilever system. So we use, we wiggle this cantilever, That puts a phase on this guy. And then we just measure the sum of the phases of these two fields. We see a signal at the wiggling frequency, shot noise here, quantum noise here. So we get a better signal to noise ratio for an array of displacements of this guy here, of this cantilever. And basically this basic prototype is we're using in all of these sensors. So here's the one of the plasmonic version, looks almost the same, right? So what we did was we took these sub-diffraction limited Hall arrays, transmitted images through them diffraction free because extraordinary optical transmission. Don't have time to go into this, but it can support a wide array of K vectors and transmit a large number of spatial modes, essentially diffraction free through this sub-diffraction limited Hall array. So what we did was we took plasmonic thin films and excited plasmons on two separate films, but which supported the same optical frequencies. Then we detected the amplitude and phase on the output of these things to see how the plasmons change the amplitude and phase of these optical fields. And at the same time, we put some pretty pictures on them. And what we see is that, so this is a sinusoidal variation in amplitude and phase noise, where this dashed line is coherent noise. So this looks a little bit complicated to understand what's going on here, but believe it or not, what these pictures are telling you is that these images of these O's and U's, after our friends at University of Oklahoma who we worked with, are entangled with each other. So whenever you see simultaneous noise reduction in one of in these two curves simultaneously, so amplitude and amplitude difference in phase sum, you have entanglement that is similar in characteristics to the Einstein-Felsky-Rosen paradox. So we're using plasmons to transmit information, quantum information contained in these images through these plasmonic Hall arrays and maintaining entanglement on the other side, which we kind of make a leap and say, well, more characterization is needed, but it sounds like these localized surface plasmons that were used to make this image were entangled with one another. The photons that went in and were annihilated were entangled, and the photons that were re-emitted and came out were still entangled with each other. So that was quite interesting. So we used that same effect to, I think this is the last couple of slides, we use that same effect to measure ultrasound waves. So everybody here today has actually presented sensing of actual things. So I have to present some actual sensing that we've actually done here rather than just phenomenological devices. So here we built a little chamber that lets us control local air pressure around the plasmonic film with ultrasonic transducers. And then we just ask how well can we measure the pressure inside this chamber based on this ultrasound amplitude the ultrasound wave is applied. And of course, the figure of merit is index of refraction changes. And so first of all, we show that we can, oh, it's got cut off a little bit. We can resolve signals that are smaller than the shot noise. And we show that for a very small index of refraction changes, down here we get a higher confidence level with the quantum noise reduction measurement, of course. So we go from, if we're being charitable and saying that we only need a 99% confidence interval, we're getting a fair, so this is about a 40% reduction. And we end up within the bandwidth of our detector, actually a 1 Hertz bandwidth, we get about a part in 10⁻⁻10 refractive index units in this sensor. So that was nice to show in proof of principle improvement in refractive index units measurements with squeeze light. We also did same thing with Kretschmann configuration. I'll let you, if you want to look at these papers, and because I'm gonna have to stop and get questions now. This is just measuring index of refraction shift again, where every single data point in all of these curves has squeezing in it. This is the raw data here showing squeezing in every single data point here. And so we're able to measure transmission along these curves a little bit better than we can with the classical. And that was, let me skip forward real quick. That was good enough to get on the cover of ACX Photonics a few years ago. So, you know, we're just doing that ad nauseum. So I'll stop here and see if anybody has any questions here. I see something in chat.